So, first thing we look at, Bronsted-Lowry acids and bases. Okay, now this is not one guy, these are two separate guys, and they came up with the idea of what acids and bases should be around the same time. Okay, so, Bronsted-Lowry said, you know, there's these things that don't produce H plus ions and OH ions in water, like Arrhenius said, but they still have the properties of acids. So, they both said, well, what an acid actually does is it's a proton donor. Okay? And a base is a proton acceptor. And they do not need to be aqueous for the substances to be acids or bases. Okay? Now, why are they talking about protons? Okay? Well, take a look at this thing right here, the hydrogen ion. Remember, hydrogen has basically one proton and one electron surrounding it. Oops. Okay, and what happens when you make a hydrogen ion? Take away the electron, which basically just means that all you have is a proton left over when we're talking about the hydrogen ion. So when we say proton donor, we're actually talking about hydrogen ions. Okay. Now, whenever you have a Bronsted-Lowry acid, you also have to have a Bronsted-Lowry base present, because in order for an acid to act like an acid, you have to have a transfer of protons. Okay. Now, the substance that is produced after Bronsted-Lowry acid transfers or loses its proton is now a base. Okay. And likewise, and we call this thing the conjugate base of that acid. Okay. And the substance that is produced when a base accepts a proton is now acidic. Okay, and this is the conjugate acid of that base. So, here's an example. Okay, so this thing here you should recognize as nitrous acid. Okay, and we notice that we have water here. Okay, now, what happens in this, and this, since this is an acid, it still must be an acid no matter whose definition you're talking about. Okay, what happened? Well, remember, it actually does not produce H+, it produces H3O+, by a transfer of a proton, the H+. Okay, so when you donate the H+ to that, that means that this substance must be the acid, and water is the substance that's gaining it, so it's actually going to be a base. Okay, now, what did water turn into? The water turned into H3O+. So this base produces a conjugate acid. Okay, and what happened to the nitrous acid? Well, it turned into this substance here. So this substance right here must be a base, and this is the conjugate base. Okay, so what was the acid? HNO3. What was its conjugate base? NO2-. What was the base? Water. What was its conjugate acid? Hydronium ion. Okay, so a base produces an acid, and an acid produces a base. Base produces the acid produces the base. Okay, let's look at something else here. Okay, now this substance here, you look at it and you go, I don't know what that is. Doesn't look like an acid or a base. But let's look and see what happens. It produces this ion here. How did that happen? Okay, well, the water had to donate an H+ to this. So since that's donating, water must be the acid, and this is accepting, so this substance here, known as methylamine, is the base. Okay, now, on the right side, and notice the conjugate things can only be on the right side. Okay, so what did this come from? It came from a base. So that means this must be the conjugate acid. Okay, and you notice that thing there, hydroxide. Well, that must be a base. It has to be a base. So this must be the conjugate base. Okay, so when they say list the acid conjugate base or base conjugate acid, the base and its conjugate acid are right here. the acid and its the base and its conjugate acid are right here. The acid and its conjugate base are here. Okay, so, and they can only be different by an H plus. Okay, notice the difference between this one right here and this one right here. They're only different by an H plus. Same with the acid and the base. Okay, now take a look. Water is a base, and water is also an acid. So what's water? Okay, well, there's some substances can act as amphoteric substances. Okay, what is an amphoteric substance? It can act as either acid or a base, but not at the same time. It has to be in different reactions. Okay, so an example, well, we saw water. Okay, what's water going to do? Well, that's an acid, right? HCl, hydrochloric acid. So water must be acting as the base here. What happens? It turns into H3O plus and Cl minus. Okay, oops, let's clear that for a second. Okay, now what's happening here? Well, you guys should know ammonia. Ammonia is an acid, or sorry, ammonia is a base, so it's going to accept H plus. Okay, how do you know? Again, remember the little trick. If you're not sure, donate an H plus or remove an H plus from the water and see whatever you produce. Does it produce something you've seen before? When you donate an H plus to NH3, you end up with NH4 plus. The water loses an H plus, ends up with OH minus. So since the water is donating, it's going to be the acid. Okay. Now, we don't have water here, but this is another amphoteric substance. This is the bisulfate ion. It can give up an H plus there, and you end up with SO3 minus and H2O. Okay, so in that case, it's acting as an acid. Okay, is it amphoteric? Yeah. Why? Well, what happens if you try and put it in an acidic solution? It will accept the H plus and turn into H2, SO3 plus H2O. Okay, so in this case, it's acting as a base. It's accepting the H plus. Okay, now Lewis came along. Lewis, you guys have seen his name before in Lewis dot structures. And remember, Lewis said the dots were representing electrons. So Lewis said, well, you know what? There's some things that still act like acids and bases and don't fit the categories of either Arrhenius or Bronsted-Lowry. Okay, so he said, well, it's because it deals with electrons. So Lewis acids and bases. Same guy came up with the Lewis dot structures. An acid is an atom-ion molecule that will accept an electron pair and can end up forming coordinate covalent bonds when it does. Okay, and the base is going to be the thing that donates electron pairs. Okay, be careful. Remember, if a substance donates hydrogen ions, it was an acid. And if it accepted hydrogen ions, it's a base. But when we talk electron pairs, it's the opposite. Okay, so what's an example? Okay, well, this substance here, we just said ammonia must be a base. It's a base under one definition, has to be a base under everyone's definition. Okay, now BF3 doesn't look like it's going to be able to do anything under Arrhenius or Lewis's definition, but this is a really acidic substance. Okay, why? Well, what's it like to do? Look at the Lewis structures. Okay, boron trifluoride. Remember, boron only has 3 valence electrons, so it can only make 3 bonds like that. Okay, but it's highly reactive because it wants that 4th pair of bonds. That should be going right here. Okay, ammonia has the extra pair of bonds. So what can it do? It can make that coordinate covalent bond. Okay, what happens? You end up with the boron with a coordinate covalent bond between the nitrogen. The hydrogens are here. The The fluorines are here. Okay, so boron really likes to attract those electrons. Okay, so that means boron will be the base. The ammonia is the boron will be the acid rather, and the ammonia is the base. Okay, now is this still going to be an acid, and is that still going to be a base under Arrhenius or under Lewis's definition? Yeah, simple. Why? Hydrogen ion has no electrons. The hydroxide has 1, 2, 3 pairs of non-bonding electrons. So what happens? H plus and OH minus produce this bond right here. This pair donates that way, and you make a bond right here. Doesn't look very happy, does he? Okay, so you can kind of think of acid-base definitions this way. Arrhenius acids and bases, these are going to be the smallest definitions. Okay, and the smallest group, the most concise group. What happens? They donate H pluses or OH minuses in water. Okay, Bronsted-Lowry, both of them deal with the hydrogen ion, either donating for an acid or accepting for a base. Lewis acids and bases basically dealt with electron pairs. Okay, and donating and accepting. Don't forget, the definitions are kind of the opposites though. Here a donor is the base and the acceptor is the acid. Here the donor is the acid and the acceptor is the base. Okay, so now take a look. Which of these would be a Bronsted-Lowry acid but not an Arrhenius acid? In other words, which of those would fall in this category out here?